TCP/IP is fast becoming the de facto data communications protocol of choice for network designers. Its dominance is primarily driven by its use within the Internet. This module is designed to give an overview of the TCP/IP protocol suite and to outline associated processes such as IP routing. This module should be completed before proceeding with the more in-depth studies of the Internet and IP services contained in the other modules on this CD. In the first section of this training module, we will examine the history behind the development of the TCP/IP protocol suite, from its early definition by the US Department of Defense to its dominant use in today's business-critical Internet. We will investigate the regulation of the protocol suite's development and the benefits provided in adopting a layered approach to these developments. In later sections, we will investigate in more detail the components of the Internet protocol, how this can be used to transmit information between computers, and how the transmission control protocol can guarantee a secure end-to-end service for this information transfer. Finally, we will investigate a number of standard application processes that can make use of TCP/IP transmissions. The development of the TCP/IP protocol suite and the Internet go hand in hand. This slide, however, focuses on the main events associated with TCP/IP's development. For more on the development of the Internet, see the associated module on the Internet development. The Internet, as we know it today, traces its origins back to a Defense Department project in 1969. The subject of the project was wartime digital communications. At that time, the telephone system was about the only theater-scale communications system in use. A major problem had been identified in its design, its dependence on switching stations that could be targeted during an attack. Would it be possible to design a network that could quickly reroute digital traffic around failed nodes? To achieve a working solution, the Defense Advanced Research Projects Agency, DARPA, launched the DARPA Internet Program. The resulting Advanced Research Agency network, ARPANET, went live in 1969. The ARPANET, largely the plaything of academic and military researchers, spent more than a decade in relative obscurity. As Vietnam, Watergate, the oil crisis, and the Iranian hostage crisis rolled over the nation, several Internet research teams proceeded through an evolution of protocols. The idea of open architecture networking was first introduced at DARPA in 1972. The existing network control protocol, NCP, did not have the ability to address networks and hosts further downstream than a destination switch on the ARPANET. Thus, DARPA decided to develop a new version of the protocol which could meet the needs of an open architecture network environment. This protocol would eventually be called the Transmission Control Protocol Internet Protocol, TCP/IP. While NCP tended to act like a device driver, the new protocol would be more like a communications protocol. In 1979, the Internet Control and Configuration Board, ICCB, was formed. Their charter was to provide an oversight function for the design and development of protocols, including TCP/IP, within the Internet. In 1983, this was renamed the Internet Activities Board, IAB, and the Internet Engineering Task Force, IETF, was added in 1984. Development on TCP/IP continued after its initial definition. The most common versions of TCP and IP, in fact, date back to 1981. In 1982, the Department of Defense declared that TCP/IP would become the new standard ARPANET protocol suite, and the official cutover occurred on January 1st, 1983. An even bigger boost for TCP/IP came from the University of California at Berkeley in 1983, when TCP/IP was bundled with their version of Unix. Domain naming via use of domain name servers was introduced in 1987. Until then, host names were mapped to IP addresses using static tables, but the Internet's exponential growth had made this practice infeasible. the early 90s, the first address exhaustion crisis hit the Internet technical community. The present solution, Classless Interdomain Routing, CIDR, will sustain the Internet for a few more years by making more efficient use of IP's existing address space. For a more lasting solution, IETF is looking at IP version 6 and its larger address space, but CIDR is here to stay. In the late 1980s, many large corporations found themselves thrust into a multi-vendor computing and communications environment. Such an environment was brought about primarily by the autonomy of work groups in the purchase of local area networks, LANs, and associated applications, but also due to mergers and acquisitions. As users began to need access to the resources of other work groups, the requirement to interconnect LANs on a company-wide basis emerged. None of the major computer vendors, for example IBM and DEC, offered a model for communications that supported connectivity and interoperability among many different vendors' equipment. Hence, network managers were required to operate multiple computer networks, each with their networking protocols. Corporate information systems managers began to search for a model for multi-vendor interconnection, and soon discovered the Internet model and its foundation, the TCP/IP protocol suite. They began building structures based on the Internet model, using the protocols developed within that environment. Hence, networks today are converging on a model built around the Internet and the TCP/IP protocol suite in particular. This networking trend towards everything TCP/IP has had a dramatic impact on the internetworking marketplace. Traditional multi-application networks running on multiple protocols such as IBM SNA and Novell IPX are migrating to operate on an all TCP/IP environment. In a recent Forrester survey of 50 top US companies, there has been a dramatic increase in the use of TCP/IP. The number of companies reporting networks with more than 50% of applications on IP has risen from 18% in 1996 to 82% in 1998, and this trend is set to continue. The convergence of data networking towards exclusive use of TCP/IP is only the start. Recently, the press and TV have carried article after article on the emergence of IP's support for traditional circuit switch services such as video and voice. For example, Microsoft now ships desktop video conferencing over IP as part of its Windows 98 OS package. Whole new companies are starting up based on the ability of IP to carry traditional voice cheaper than existing voice networks. An understanding of such an important and market-shaping protocol suite is now essential for anyone involved in telecommunications. The Internet Architecture Board, IAB, was formed in 1983 to coordinate and guide the design of internetworking protocols and development of the Internet. The board is responsible for publishing all protocols and standards and initiates the procedures by which all standards are developed. The IAB is divided into various areas responsible for a range of topics to do with researching and development. The research is covered by the Internet Research Task Force, IRTF. Developments are controlled by the Internet Engineering Task Force, IETF. The IETF is split into various work groups to study different aspects of the TCP/IP protocol suite. Request for comments, or RFCs, are documents that define all protocols, standards, assigned numbering schemes, and general information related to the TCP/IP protocol suite and the Internet in general. There are currently over 2,000 RFC documents that are available via postal mail, electronic mail, file transfer, and via the web from the Network Information Center, NIC, operated by the IAB. RFCs are numbered sequentially as they are published. Draft RFCs are called appropriately Internet drafts. As an RFC undergoes revision, the newer version is given a new RFC number and supersedes previous versions. For example, RFC 793 describes the Transmission Control Protocol, TCP. This RFC supersedes the earlier versions of TCP numbered 761 and 675. Draft RFCs can be submitted by anyone. Vendors, users and service providers lead the working groups within the IETF. As a quick aside, a lot of good technical humour can be found in any draft RFC dated the 1st of April. In the early 1980s, the International Standards Organization, ISO, generated a 7-layer model into which existing and new standards could be added. The 7-layer model is an example of a stacked architecture. The idea is based around a modular approach. If you have a standard defining a protocol that operates at one layer and is designed to carry out certain functions, then it is feasible to have many layers, the total of which provides for all the connection and communications elements required. To add more flexibility to the model, each layer is designed to operate independently of the others. Should any change need to be made to the network, that layer of the technology can be replaced without impacting on the operation of the existing upper and lower layers. The US Department of Defense, DoD, originally defined the TCP IP protocol within their reference model used on ARPANET. The DoD model is a 4-layer model. The comparison of the two models shows that the two are similar in concept, but have a different number of layers with different names. While similar things happen at similar places, the specification on how these things happen are different. This leads to a very different suite of protocols for the DoD model. As already discussed, each layer of the stacked architecture operates independently of the others. This is achieved using a method referred to as encapsulation. Each layer communicates to its adjacent layers using well-defined service access points, or SAPs. Any layered protocol can be developed independently of adjacent layers as long as its data is received or sent via these SAPs. The layer receiving data from the layer above will process the data, add its own protocol header, and transfer the data block to the layer below. The layer below will simply treat the data as a block. It will not try to understand its meaning. This process is undertaken at all layers by the sending device. At the receiving device, the reverse happens. When data arrives, the first layer processes its peer header and then passes the data to the layer above, which carries out the same action. When the TCP IP protocol suite was first developed, it was as one large protocol that incorporated all facilities. Since 1979, the functionality has been split up and a 4-layer architecture has been deployed. The network access layer is the lowest layer and is dependent on the type of networks that a device is connected to. The TCP IP protocol suite does not define any particular network access protocols, but there are RFCs recommending how TCP IP uses Ethernet, FDDI, frame relay, X25, and even ATM. The layer is responsible for transferring data from one device on a network to any other on the same network, e.g. from a host to a router. The Internet layer is the layer at which the Internet protocol, IP, resides. The function of this layer is to deliver data from any host on the Internetwork to any other host, regardless of the network or the destination. It is at this layer that routing function occurs, and so a router may not necessarily implement any higher layers. There are several protocols that can be implemented at this layer that assist IP to deliver data in the best possible way. The host-to-host layer is the end-to-end transport layer. The Transmission Control Protocol, TCP, resides at this layer to provide reliable transport to and from applications implemented at the hosts. There is an alternative protocol also at this layer called the User Datagram Protocol, UDP, which provides unreliable transport. Within the TCP IP protocol suite, applications are referred to as processes, whether or not they are designed to be used by humans or other programs. Examples of processes can be found to provide support for transferring files, email, and network management. In the next section of this training module, we will cover the details of the Internet protocol. On completion of this section, the participant will have an understanding of the IP packet structure, its control header, the format of the IP address, and how to apply masking to these addresses to achieve subnetworking. We will also investigate the future direction of IP with the planned introduction of IP version 6. The Internet Protocol, IP, provides a connectionless OSI network layer service. IP implements a datagram network. Datagrams, sometimes referred to as packets, are routed on a packet-by-packet basis from IP node to IP node. For each link and each node, IP does its best to deliver the datagram. To do this, IP defines mechanisms for datagram fragmentation and reassembly, hierarchically structuring the IP address, controlling packet lifetime in the network, and verifying the integrity of the IP header. As a connectionless protocol, IP handles each datagram individually, which means that packets can be dynamically routed around network trouble spots. Hosts do not need to establish a logical connection before exchanging IP datagrams. IP service is unreliable. It is appropriate to take a moment and reflect on the word unreliable. In an OSI context, the term unreliable refers to the fact that IP does not sequence or acknowledge datagrams, nor does it provide bit error detection or correction for datagram. There is no guarantee of delivery. If a datagram is lost, there is no indication to the end host that this has happened. It is left to the upper layers to resolve the issue. A number of adjunct protocols are associated with IP. The Routing Information Protocol, RIP, and Open Shortest Path First Protocol, OSFP, are used to determine the routing tables for IP datagrams within a network. RIP is the older of the two protocols and is currently being phased out by OSPF. The Border Gateway Protocol, BGP, is used for routing IP between networks and is particularly important in the Internet. The Internet Control Message Protocol, ICMP, defines messages used for the exchange of error and information used for diagnostic purposes. A number of protocols are defined to assist in IP address allocation and resolution. These are particularly important in building real internetworks using IP. Each will be covered in more detail in future slides. Every element of data sent by one host to another host contains an IP header. The current version of IP used in networks today is version 4. The next version of IP will be version 6. The new version of IP will provide a number of new features, not least the support for 16-byte addressing rather than the current 4-byte. The version of IP used by the host is included in the header in the version field. The header is usually a 20-byte block of control information. The header can be up to 60 bytes of information if the IP options are used. These are usually only used for network engineering. The length of the header is indicated by the Internet Header Length, IHL field, which is normally set to 5. A number of critical control fields are included in the header. The type of service, TOS field, allows the host to request that a route be used that has particular characteristics, such as low delay, high throughput, or high availability. This field is currently being modified to allow support for the new IETF class of service proposal called Differentiated Service, or DIFSER. The total length field provides a byte count of the total IP datagram, including the IP header. The identification, more fragments flag, MF, and offset fields are all used in datagram fragmentation. This process is explained on the next slide. The DF, Don't Fragment flag, can be used to indicate that a datagram must not be fragmented, even if the network requires it. If this happens, the datagram is dropped and an error message generated. The Time to Live, TTL field, is used to ensure that datagrams do not loop endlessly through a router network. When a datagram is generated by a host organization, ISO, generated a 7-layer model into which existing and new standards could be added. The 7-layer model is an example of a stacked architecture. The idea is based around a modular approach. If you have a standard defining a protocol that operates at one layer and is designed to carry out certain functions, then it is feasible to have many layers, the total of which provides for all the connection and communications elements required. To add more flexibility to the model, each layer is designed to operate independently of the others. Should any change need to be made to the network, that layer of the technology can be replaced without impacting on the operation of the existing upper and lower layers. The US Department of Defense, DoD, originally defined the TCP/IP protocol within their reference model used on ARPANET. The DoD model is a 4-layer model. The comparison of the two models shows that the two are similar in concept, but have a different number of layers with different names. While similar things happen at similar places, the specification on how these things happen are different. This leads to a very different suite of protocols for the DoD model. As already discussed, each layer of the stack architecture operates independently of the others. This is achieved using a method referred to as encapsulation. Each layer communicates to its adjacent layers using well-defined service access points, or SAPs. Any layered protocol can be developed independently of adjacent layers as long as its data is received or sent via these SAPs. The layer receiving data from the layer above will process the data, add its own protocol header, and transfer the data block to the layer below. The layer below will simply treat the data as a block. It will not try to understand its meaning. This process is undertaken at all layers by the sending device. At the receiving device, the reverse happens. When data arrives, the first layer processes its peer header and then passes the data to the layer above, which carries out the same action. When the TCP/IP protocol suite was first developed, it was as one large protocol that incorporated all facilities. Since 1979, the functionality has been split up and a 4-layer architecture has been deployed. The network access layer is the lowest layer and is dependent on the type of networks that a device is connected to. The TCP/IP protocol suite does not define any particular network access protocols, but there are RFCs recommending how TCP/IP uses Ethernet, FDDI, frame relay, X25, and even ATM. The layer is responsible for transferring data from one device on a network to any other on the same network, e.g. from a host to a router. The Internet layer is the layer at which the Internet protocol, IP, resides. The function of this layer is to deliver data from any host on the Internetwork to any other host, regardless of the network or the destination. It is at this layer that routing function occurs, and so a router may not necessarily implement any higher layers. There are several protocols that can be implemented at this layer that assist IP to deliver data in the best possible way. The host-to-host layer is the end-to-end transport layer. The Transmission Control Protocol, TCP, resides at this layer to provide reliable transport to and from applications implemented at the hosts. There is an alternative protocol also at this layer called the User Datagram Protocol, UDP, which provides unreliable transport. Within the TCP/IP protocol suite, applications are referred to as processes, whether or not they are designed to be used by humans or other programs. Examples of processes can be found to provide support for transferring files, email, and network management. In the next section of this training module, we will cover the details of the Internet protocol. On completion of this section, the participant will have an understanding of the IP packet structure, its control header, the format of the IP address, and how to apply masking to these addresses to achieve subnetworking. We will also investigate the future direction of IP with the planned introduction of IP version 6. The Internet Protocol, IP, provides a connectionless OSI network layer service. IP implements a datagram network. Datagrams, sometimes referred to as packets, are routed on a packet-by-packet basis from IP node to IP node. For each link and each node, IP does its best to deliver the datagram. To do this, IP defines mechanisms for datagram fragmentation and reassembly, hierarchically structuring the IP address, controlling packet lifetime in the network, and verifying the integrity of the IP header. As a connectionless protocol, IP handles each datagram individually, which means that packets can be dynamically routed around network trouble spots. Hosts do not need to establish a logical connection before exchanging IP datagrams. IP service is unreliable. It is appropriate to take a moment and reflect on the word unreliable. In an OSI context, the term unreliable refers to the fact that IP does not sequence or acknowledge datagrams, nor does it provide bit error detection or correction for datagram. There is no guarantee of delivery. If a datagram is lost, there is no indication to the end host that this has happened. It is left to the upper layers to resolve the issue. A number of adjunct protocols are associated with IP. The Routing Information Protocol, RIP, and Open Shortest Path First Protocol, OSFP, are used to determine the routing tables for IP datagrams within a network. RIP is the older of the two protocols and is currently being phased out by OSPF. The Border Gateway Protocol, BGP, is used for routing IP between networks and is particularly important in the Internet. The Internet Control Message Protocol, ICMP, defines messages used for the exchange of error and information used for diagnostic purposes. A number of protocols are defined to assist in IP address allocation and resolution. These are particularly important in building real internetworks using IP. Each will be covered in more detail in future slides. Every element of data sent by one host to another host contains an IP header. The current version of IP used in networks today is version 4. The next version of IP will be version 6. The new version of IP will provide a number of new features, not least the support for 16-byte addressing rather than the current 4-byte. The version of IP used by the host is included in the header in the version field. The header is usually a 20-byte block of control information. The header can be up to 60 bytes of information if the IP options are used. These are usually only used for network engineering. The length of the header is indicated by the Internet Header Length, IHL field, which is normally set to 5. A number of critical control fields are included in the header. The type of service, TOS field, allows the host to request that a route be used that has particular characteristics, such as low delay, high throughput, or high availability. This field is currently being modified to allow support for the new IETF class of service proposal called Differentiated Service, or DIFSER. The total length field provides a byte count of the total IP datagram, including the IP header. The identification, more fragments flag, MF, and offset fields are all used in datagram fragmentation. This process is explained on the next slide. The DF, Don't Fragment flag, can be used to indicate that a datagram must not be fragmented, even if the network requires it. If this happens, the datagram is dropped and an error message generated. The Time to Live, TTL field, is used to ensure that datagrams do not loop endlessly through a router network. When a datagram is generated by a host, a value is placed in this field, usually 32, 64, or 255. Every router that receives this datagram decrements this field by 1. Should a router receive a datagram, decrement this field by 1, and the count equals 0, then the datagram is considered lost and is discarded. The protocol field provides a pointer as to which higher layer protocol the data field should be passed to next. Common values are 6 for TCP, 17 for UDP, and 1 for ICMP. The header checksum is a very simple checksum performed on the header only. The checking of data is presumed to be the responsibility of higher layers. When a router receives a datagram, it will only validate the header for errors to ensure that it is routing the datagram using valid addressing. The source and destination IP address gives the addresses of the receiving and sending host. The IP address structure is discussed in detail in future slides. The size of IP datagrams may be up to 64,000 bytes in length. IP supports a packet fragmentation and reassembly capability, since the size of an actual IP transmission is limited by the underlying physical networks to which the host systems are attached and any intervening subnetworks. Assume a host based on an Ethernet network with a maximum frame size of 1500 bytes transmits a single large IP datagram to a host over an IP network with a maximum IP datagram size of 1024 bytes. The IP datagram from the Ethernet won't fit. Fragmentation is an essential service that all routers and hosts support. The router always fragments, and the recipient host always reassembles. Note that a router never reassembles the datagram it is routing. The recipient host needs 3 pieces of information to reassemble the datagram correctly. The first piece of information is that all the fragments belong to the same original datagram. This is achieved by using the identifier field in the IP header. The second piece of information the host needs is to identify that all the fragments have been received. This is achieved by setting the more bit indicator in the IP header. Only once the last fragment, with more bits set to 0, have all the fragments been received. Finally, the host needs information that all the fragments can be reassembled in the right order. This is achieved using the offset field in the IP header. This allows the host to reorder the fragments should they arrive in the wrong order. The first fragment contains 1024 bytes of user traffic and a 20-byte header. Hence the total length field is set to 1044. The offset is set to 0, indicating it is the first fragment. The more fragments bit is set to 0 to indicate that more fragments are still to come. The second fragment contains the remaining 476 bytes of data, so the total length is set to 496 bytes. The offset is set to 1024 to indicate that this is the second fragment, and the more fragment bit is set to 1 to indicate that this is the last fragment. In both fragments, the identifier field is set to the same number as that contained in the original datagram. With this information, the destination host can reassemble the fragments. The Arabs invented the decimal system back in the 9th century. Since then, people have loved to count using this system. However, all digital computers represent data as a collection of bits. A bit is the smallest possible unit of information. It can be in one of 2 states, off or on, 0 or 1. The meaning of the bit, which can represent almost anything, is unimportant at this point. The thing to remember is that all computer data, a text file on disk, a program in memory, a packet on a network, is ultimately a collection of bits. The binary system is the representation of numbers using 2 states, or base 2. Simple binary numbers can easily be represented using 1s and 0s, but large binary numbers are hard to write. Computer scientists often write them using hexadecimal or base 16 notation. This is often called hex. When considering IP addresses, it is important that you can understand hex notation and convert from binary to hex to decimal. A common and convenient grouping of bits is the byte or octet, composed of 8 bits. Obviously, if a byte has 256 possible states, its exact state can be represented by a number from 1 to 256. However, since 0 is a very important number, a byte is more typically represented by a number from 0 to 255. This is very common, and with bit pattern 00000000 representing 0, and bit pattern 11111111 representing 255. The numbers matching these 2 patterns, and everything in between, can be computed by assigning a weight to each bit, multiplying each bit's value, 0 or 1, by its weight, and then adding the totals. For example, Here's how 250 is represented in binary: 11111010. If hexadecimal is the representation of numbers using base 16, how do you represent numbers from 10 to 15? You use letters A through F. This is important as it allows you to represent binary in shorthand. The binary number 11111010 can simply be written as FA. Conversion to decimal can now be achieved easily using multiples of 16. FA is equal to 16 times 15 plus 10 times 1, which equals decimal 250. Each device attached to any IP-based network must be given a unique address. These must be assigned at configuration time or dynamically at boot up. These addresses are carried in the header of all information transmitted over the network to identify the source and destination computers. The current IP version, IPv4, defines 32-bit, 4-byte addresses, which permit over 4 billion computers or hosts to attach to a single internetwork. IP addresses are represented in a format known as dotted decimal, where each byte is represented by its decimal equivalent, and the 4 numbers are separated by a dot. With 8 bits, you can represent numbers between 0 and 255. Therefore, the IP address, represented in binary as 100000000, 01000011, 001001110, 000101111, is written and spoken in the easier-to-remember dotted decimal notation as 128.67.38.23. The IP address space is flat with a 2-part division. Each IP address has 2 components, a network identifier, or net ID, and a host identifier, host ID. The net ID identifies the specific subnetwork to which the computer is attached. The host ID uniquely identifies a particular computer within that subnetwork. To make sure that there is never any duplication of network numbers in the Internet, all networks must obtain an official net ID from the Internet-assigned number authority if they wish to connect their network to the Internet. The allocation of address bits between the net ID and host ID will determine how many subnetworks can be defined and how many computers can be attached to a particular network. In order for IP addresses to be relevant to the type of network that they're associated with, the IAB developed classes of address that are chosen depending on the size of the network. To strike a balance between efficient use of the address space and the needs of different networks, 5 classes of address were defined, designated Class A through Class E. The 3 main classes of interest to us are A, B, and C. The essential difference between these classes is the different sizes of the net ID and host ID fields. Class A addresses, indicated by a 0 in the first bit of the address, have an 8-bit net ID and a 24-bit host ID. There are only 126 possible Class A addresses, as the net ID can only be 1 to 127. Thus, a Class A address is intended for use in very large networks, since the 24-bit host ID can uniquely identify over 4 million computers. Most of the possible Class A addresses have already been allocated. Class B addresses, indicated by a 1 followed by a 0 in the first 2 bits of the address, have a 16-bit net ID and a 16-bit host ID. Subnetworks can support up to 65,534 computers, and there are 16,382 possible addresses. Again, we can see that the restriction of the first 2 bits to 1 and 0 respectively limits the total number of Class B networks to 16,382. The Class B address is intended for moderate-sized networks. Well over 2/3 of the possible Class B addresses have now been allocated. Class C addresses, defined by 2 ones followed by a 0 in the first 3 bits of the address, are intended for small subnets. Class C addresses have a 24-bit net ID and an 8-bit host ID, yielding over 2 million possible addresses. Each network can support up to 254 computers. Most companies who now request a new Internet address are provided Class C addresses. If they require support for more than 254 hosts, then they are provided multiple Class C addresses. Only when they need more than 16 Class C addresses are they given a Class B address. No organization, when it secures a Class A or B address, plans to deploy a single LAN with over 16 million for Class A or 65,000 for Class B hosts. Instead, the organization needs to further allocate the address space to regions, divisions, departments, and so forth. The mechanism to do this is called the subnet mask. A mask is an electronic filter used to extract particular portions of a data field. A subnet mask is used to extract the net ID from the IP address. The subnet mask uses the logical AND operation. Each bit in the IP address is ANDed to the corresponding bit in the subnet mask. If both bits are 1, the result is 1. Any other combination results in 0. This is the equivalent of mathematical addition. The subnet mask has the effect of clearing, i.e. setting to 0, all of the bits corresponding to the host ID. In the example shown, the IP address 150.128.110.1 is ANDed with the subnet mask 255.255.0.0. The result of this process is the new value 150.128.0.0. We effectively zeroed out the host ID, leaving only the net ID. By using this mechanism, an organization can break free of the strict rules of IP address classes and allocate addresses from the pool as needed. In effect, this is done by borrowing some of the host ID bits and making them part of the net ID. Consider the following example. Assume that Company X has been assigned Class B address 128.56.0.0 and wishes to establish a number of small networks, each with less than 255 hosts. The company would like to treat their Class B address as a collection of Class C addresses. To accomplish this, the company partitions the address by telling each department which value to use in the third byte of the address and to use the subnet mask 255.255.255.0. Now, Finance Department will use 128.56.34.0 and Sales will use 128.56.22.0. The subnet mask is used to find the net IDs, which are now 128.56.34 and 128.56.22 respectively. This will greatly simplify the task of the routers. Rather than having to learn about 16,000 hosts, the router only needs to find 254 subnets. Back in the mid-1990s, with a new network being connected to the Internet every 30 minutes, the Internet was faced with 2 critical problems. It was running out of IP addresses, and the routers in its backbone were running out of capacity in their global routing tables. Because Internet addresses were generally only assigned within the 3 class sizes, there were a lot of wasted addresses. For example, if you needed 100 addresses, you would be assigned the smallest address, Class C, but that still meant 154 unused addresses. The overall result was that while the Internet was running out of unassigned addresses, only 3% of the assigned addresses were actually being used. A related problem was the sheer size of the Internet global routing tables. As the number of networks on the Internet increased, so did the number of routes. A few years back, it was forecast that the global backbone Internet routers were fast approaching their limit on the number of routes they could support. Even using the latest router technology, the maximum theoretical routing table size is approximately 60,000 routing table entries. If nothing was done, the global routing tables would have reached capacity by mid-1994, and all Internet growth would be halted. Classless interdomain routing, CIDR, is a replacement for the old process of assigning class A, B and C addresses with a generalized network prefix. Instead of being limited to network identifiers or prefixes of 8, 16 or 24 bits, CIDR currently uses prefixes anywhere from 19 to 27 bits. Thus, blocks of addresses can be assigned for networks as small as 32 hosts up to networks with over 500,000 hosts, allowing for address assignments that much more closely fit an organization's specific needs. A CIDR address includes the standard 32-bit IP address and also information on how many bits are used for the network prefix. For example, in the CIDR address 206.13.01.48/25, the /25 indicates the first 25 bits are used to identify the unique network, leaving the remaining bits to identify the specific host. The CIDR addressing scheme also enables route aggregation, in which a single high-level route entry can represent many lower-level routes in the global routing tables. The scheme is similar to the telephone network, where the network is set up in a hierarchical structure. A high-level backbone network node only looks at the area code information and then routes the call to the specific backbone node responsible for that area code. The receiving node then looks at the phone number prefix and routes the call to its subtending network node responsible for that prefix, and so on. The backbone network nodes only need routing table entries for area codes, each representing huge blocks of individual telephone numbers, not for every unique telephone number. Currently, big blocks of addresses are assigned to the large Internet service providers, ISPs, who then reallocate portions of their address blocks to their customers. For example, an ISP might be assigned a CIDR address block with a prefix of /15, equivalent to 512 Class C addresses or 131,072 host addresses, and typically assigns its customers CIDR addresses with prefixes ranging from /27 to /19. These customers, who may be smaller ISPs themselves, in turn reallocate portions of their address block to their users and/or customers. However, in the global routing tables, all these different networks and hosts can be represented by the single Internet route entry. In this way, the growth in the number of routing table entries at each level in the network hierarchy has been significantly reduced. Currently, the global routing tables have approximately 40,000 entries. It is worth spending a moment to examine where IP address assignments come from and how they are assigned within an IP-based internetwork. First off, anyone can select their own IP address if they are on a private network. However, there is almost nothing to be gained by doing this. If you build a private IP network with a random IP address, what happens if you later decide to connect to the Internet? Invariably, you will have to renumber your computers. When attaching to the Internet, as already stated, net IDs are assigned by the Internet Assigned Number Authority, IANA. The IANA assigns net IDs to individual organizations or to Internet service providers who in turn assign them to their customers. With a few exceptions, the recommended source for an address assignment today is the customer's ISP. Under this scenario, the customers are only renting the address, and if they change ISPs, it is strongly recommended that they get a new address from their new ISP and renumber all their network devices. Host IDs are assigned locally by an address administrator. This function is essential to ensure that duplicate addresses are not assigned within an organization, just as IANA ensures that duplicate net IDs are not assigned. IP addresses themselves are not assigned on a per-device basis, as the name host ID might imply, but on a per-port or attachment basis. This means that some equipment is administratively part of multiple networks and has multiple IP addresses. In this simple network, Site 1, the LAN on the left, has an assigned Class C net ID 199.182.20. The two PCs and the router on the LAN have been assigned host IDs 17, 5 and 100 respectively. This LAN is attached to some wide area network or WAN service provider which has an assigned Class B net ID 142.100. The WAN has assigned the Site 1 LAN router a host ID of 81.54, so that the router's WAN port has an IP address of 142.100.81.54. Hence the router in effect has two IP addresses, one for each of its physical ports. A similar scenario can be found at Site 2, where a customer's host system is directly attached to their own router. Again, the router has two IP addresses because it is part of two different systems. Finally, the host at Site 3 has a host ID directly assigned from the WAN service provider's address space. This represents a host that is actually a part of the WAN. In the connectionless datagram environment of IP, each host and node acts autonomously. Datagram delivery is on a best efforts basis. Everything functions just fine as long as the network is working correctly. But what happens when something goes wrong with the network? Internet Control Message Protocol, or ICMP, is an IP-to-IP communications protocol to provide a solution to this problem. ICMP messages, delivered in IP packets, Welcome to Understanding the Internet. As has become clear over the last 2 to 3 years, the Internet represents the biggest opportunity to re-engineer our lifestyles since the invention of electricity. So what is the Internet? One definition might be that it is a global web of interconnected computer networks, a network of networks that link schools, libraries, businesses, hospitals, government agencies, research institutes and other entities into a single large communications network. The growth of the Internet and the applications it will support will touch every aspect of life, from shopping, banking, travel, sports and leisure, right into sophisticated new applications involving telemedicine, internet telephony, streaming sound and video, and many others. This module is intended to introduce you to the origins of the Internet, and to gain an understanding of the basic elements that are used to build the Internet. Further on in the module, typical Internet applications are reviewed, and some of the issues with scaling the Internet will be discussed. It is important that all participants have a basic appreciation of this material before proceeding to the more detailed subject matter. This module can be skipped for those participants already familiar with Internet basics. This training module will take participants through the evolution of the Internet. Firstly, we will review the history of the Internet and take a look at some of the key events that caused the Internet to be created. We will look at the migration of the Internet, following its development into the network and infrastructure that exists today. The Internet has come to its current state from a number of different directions. The military, commerce, education, research and... Welcome to Understanding the Internet. As has become clear over the last... What is the Internet? One definition might be that it is a global web, internet telephony, streaming sound and promote the common protocols and procedures used within the Internet. So let's take a quick look at the evolution of this unique global phenomenon.
We're rolling.
As with much technology, the history of the Internet owes its origins to
internal
the military.
speakers set.
To combat the threat posed by the USSR with its Sputnik program, the Department of Defense formed the Advanced Research Projects Agency, ARPA, in 1960, and much research was done to design networks that were resilient to single points of failure. In 1968, a company called Bolt, Beranek and Newman were funded to design and deploy a network based on packet switching technology, and in 1969, the original ARPANET became a reality. Welcome to Understanding the Internet. As has become clear over the last 2 to 3 years, the Internet represents the biggest opportunity to re-engineer our lifestyles since the invention of electricity. So what is the Internet? One definition might be that it is a global web of interconnected computer networks, a network of networks that link schools, libraries, businesses, hospitals, government agencies, research institutes, and other entities into a single large communications network. The growth of the Internet and the applications it will support will touch every aspect of life, from shopping, banking, travel, sports and leisure, right into sophisticated new applications involving telemedicine, internet telephony, streaming sound and video, and many others. This module is intended to introduce you to the origins of the Internet, and to gain an understanding of the basic elements that are used to build the Internet. Further on in the module, typical Internet applications are reviewed, and some of the issues with scaling the Internet will be discussed. It is important that all participants have a basic appreciation of this material before proceeding to the more detailed subject matter. This module can be skipped for those participants already familiar with Internet basics. This training module will take participants through the evolution of the Internet. Firstly, we will review the history of the Internet and take a look at some of the key events that caused the Internet to be created. We will look at the migration of the Internet, following its development into the network and infrastructure that exists today. The Internet has come to its current state from a number of different directions. The military, commerce, education, research and development have all played a role in the moulding and shaping of the network now called the Internet. We will then look at the current architecture of the Internet and split it up into its hierarchical elements, NAPs and maze, and the different tiers of Internet operators. Basic routing concepts will be introduced in this section. Moving on to applications, the Internet provides a number of basic capabilities that allow its users to communicate using applications like email and file transfer. These applications will be introduced in the context of current user communities. Finally, key Internet issues will look at some of the problems that have arisen due to the immense popularity of the Internet. Scaling the Internet, while still maintaining a quality of service, is a major obstacle that all vendors and service providers are continually wrestling with. Our story starts back in the 1960s, when the Cold War was at its peak. The Internet is the worldwide collection of interconnected computer networks that use a common set of protocols, procedures and formats to promote the easy and simple exchange of information. The Internet is also much more than its network connections. It's all of the individual computers connected to these individual networks, plus all the users of those computers, all the information accessible to those users, and all the knowledge those people possess. The Internet is just as much about people and information as it is about computers and computer networks. The Internet links schools, universities, companies, governments and individuals in every continent on Earth. The greatest feature of the Internet is that it is public. Anyone can connect. The Internet provides a global platform for the operation of many applications and services. Users of the Internet can exchange emails with any other user of the Internet, provided that they have an email address and that it is also known to the sender. Users can enter newsgroups and chat rooms, and they can access the almost limitless information base provided by the World Wide Web. No one person, group, government or organization owns the Internet or the data traveling on it. It is an extraordinary example of cooperation, collaboration and management by consensus, and it works. Many organizations help define and promote the common protocols and procedures used within the Internet. So let's take a quick look at the evolution of this unique global phenomenon. As with much technology, the history of the Internet owes its origins to the military. To combat the threat posed by the USSR with its Sputnik program, the Department of Defense formed the Advanced Research Projects Agency, ARPA, in 1960, and much research was done to design networks that were resilient to single points of failure. In 1968, a company called Bolt, Beranek and Newman were funded to design and deploy a network based on packet switching technology, and in 1969, the original ARPANET became a reality with a 4-node network at UCLA, Stanford Research Institute, UC Santa Barbara, and the University of Utah. In parallel with this, during 1969, AT&T were developing the early phases of Unix, and during the early 70s, Xerox were outlining Ethernet. Both technologies came to play a key role in the evolution of the Internet. In 1974, a new network protocol was specified for the ARPANET called TCP/IP to replace the old Network Control Program, NCP, that was unable to keep up with network growth. Packet switching also took another direction, X25. In 1974, BBN launched a commercial service based on X25, and in 1976, the CCITT ratified Orange Book X25. TCP/IP allowed the ARPANET to grow, and by 1995 it was up to 15 nodes. Management of this growth of traffic and associated protocols was required, and in 1979 the Internet Control and Configuration Board was formed to oversee the design and deployment of protocols in the Internet. Although work on TCP/IP started in the 70s, the most common versions were developed in 1982, and ARPANET was cut over to these in January 1983. A big boost for TCP/IP also occurred in 1983 when it was integrated with Unix in 4.2 BSD, Berkeley Software Development, part of the University of California. At the same time, the ICCB was renamed the Internet Activities Board, now the Internet Architecture Board, the de facto standards board for the Internet. The IAB was an independent standards body based in the USA. The IAB was split into two bodies in 1985, the IETF and the IRTF. The IRTF concerned itself with TCP/IP research activities, whilst the IETF concentrated on shorter-term engineering issues. 1983 also saw the start of work on the domain name system. This obviated the need for all Internet host computers to know the names and addresses of all other hosts. They could now ask the centralized DNS server to provide this information, meaning that a single database could be used and maintained for Internet host names. This was a key technical enabler for the future commercial growth of the Internet. In 1986, a major event culminated in the commissioning of a network sponsored by the National Science Foundation, NSFNet. Built as a 56 kilobit per second backbone to interconnect 4 NSF-funded networks, NSFNet grew to become a general network providing interconnection between both NSF-funded and non-NSF-funded networks. By 1989, NSFNet had grown to use T1 and T3 interconnects between sites, and was now moving into the commercial arena. During the 80s, it is true to say that the Internet was not generally used for commercial purposes. All this changed in the 90s. In 1990 saw the old ARPANET decommissioned, and in 1991 the Commercial Internet Exchange, CIX, was set up by General Atomics, UUNet and PSI to promote and supply a commercial Internet service. Also in the early 90s, newer WAN technologies like frame relay were starting to emerge, and the possibility of wide-area commercial Internet services was a possibility. NSFNet went to full T3 interconnects in 1991, and later that year new tools like Archie and Gopher were introduced. Founded in 1991, the E-Bone has provided global Internet connectivity across Europe, and more recently also in the USA. Originally established as an independent transit service provider, the E-Bone is now a wholly owned subsidiary of Global Telesystems Group. The World Wide Web, or WWW project, was conceived at CERN, the particle physics laboratory based in Geneva in 1992, as a way to interconnect sites. This concept has mushroomed, and as we all know, has had a dramatic effect on the way we access material on the web. In many ways, it was the development of the World Wide Web that turned the Internet from an academic toy to a commercial business tool. The concept of browsing and associated applications was introduced in 1993 with the Mosaic browser from NCSA, and at about the same time the Internet Network Information Center, INTERNIC project, was funded by the NSF. The INTERNIC was a project to provide information to the Internet community. It was supported by AT&T, who maintained a directory and database service, and Network Solutions, who maintained a registration service. 1994 saw the first of the network access points deployed by NSFNet, the beginnings of the architecture of the current Internet. In 1994, the NSF's Very High-Speed Backbone Network Service, or VBNS, went online, with MCI taking control of the NSF's T3 network service that had been operated by ANS. These events led to the old NSFnet being decommissioned on the 30th of April 1995. An organization called Mosaic Communications, responsible for one of the first Internet browsers, went public in 1995 and was well received by the industry and analysts. Their stock prices jumped by 250% on their first day of trading, and by year-end had captured about 65% of the browser marketplace. Mosaic were later renamed Netscape Communications, and by the late 90s have grown into one of the largest vendors of Internet browser technology. In 1996, about 10 million hosts were connected to the Internet, rising to about 16 million in 1997. The number today is about 45 million and continuing to grow at an almost exponential rate. To accommodate this growth, Internet backbone technology is continuing to advance. In the USA and in the major countries of Western Europe, the norm in 1996 were networks operating with backbone speeds of 155 or 622 megabits per second. Within many backbone provider networks, these are now being upgraded to 2.5 gigabits per second, with 10 gigabits per second under review in some instances. For example, in Europe, both the GTS eBone and UUNet network capacities have recently been increased to 2.5 gigabits per second using combinations of SDH and DWDM technologies. Refining and directing developments of existing and new protocols is the responsibility of the IETF, an independent body. The IETF are a proactive organization driven by the needs of the user community. Compared to the older regime of the CCITT, now the ITU, of producing standards every 4 years, the IETF can propose, ratify and supersede a standard in less time than that. The IETF coordinates the production of Request for Comments, or RFCs. These are technical papers defining the creation and refinement of new protocols and services. RFCs span a wide variety of topics. Even technical humor can be found in RFCs dated the 1st of April. There is no time dependence to the generation of RFCs. They can be submitted into the process at any time, resulting in a more modern and fast-moving Internet than would otherwise be the case. RFCs go through a number of stages that are shown here. At any time, refinements can be made to the proposal, and an RFC is not complete until it has been ratified by the IETF and moved to official standard status. RFCs are referenced by number, and remember that a revised standard is always assigned a new number. When ordering an RFC for any standard, always ensure you ask for the highest numbered RFC listed against that standard. Although RFCs can be obtained in paper format, the most convenient method is to get them directly from the IETF website at www.ietf.org. As mentioned, in 1995, the old ARPANET ceased to exist, and the Internet moved into a new commercial era. Whereas the ARPANET had been based on government funding, the NSF proclaimed their intention that the Internet should become self-funding. This meant that the gates to commercialization were opened. Regional networks became self-supporting, leading to increased competition, price cutting, and the start of acquisitions and mergers amongst the Internet service providers, or ISPs. A new architecture started to become evident, based around network access points, or NAPs. These were locations where operators and ISPs could exchange traffic between their networks that were starting to form the Internet. This next section takes a look at the architecture of the Internet, starting with the basic hierarchy. Initially, the Internet was defined by a hierarchical routing architecture that was primarily based on the centralized routing scheme that had been used in the old ARPANET. The core backbone was based on the old ARPANET switches, which were used for data exchange between access networks. Special routers were used in the backbone that supported gateway-to-gateway protocol, or GGP. GGP collected routing information from the access networks connected to the backbone and distributed it to other routers that were interested in finding a way to another network, much in the same way as a person would do with an index and a book of maps. The core routers communicated to exterior gateway routers using EGP, or Exterior Gateway Protocol. The exterior gateways would act as the interface to an autonomous system, or AS, which is a group of networks and gateways with its own protocols for collecting and distributing routing information. OSPF, a modern routing protocol, uses the term autonomous system, AS, to describe any collection of networks and routers under a common network administration. In the Internet, an AS distinguishes a private network from the public backbone. It is generally true that an AS uses a single routing protocol. In the early Internet, there were many such protocols, such as ALOA, NCP, etc. As we shall see, the Internet now operates very successfully using no more than 3 or 4 routing protocols. The current model of the Internet has moved on significantly from the old days of the ARPANET. There is no single provider of the Internet backbone any longer. It is a collection of IP services from multiple suppliers. The example here shows 3 backbone providers, but there are others. As we shall see in a later slide, there are over 30 different providers of backbone services, and the list changes daily, and new entrants come onto the marketplace with new services. Connection between these backbone providers occurs at interchange points called NAPs, Network Access Points. Sometimes these are referred to as MEAs, Metropolitan Area Exchange, or sometimes Metropolitan Area Ethernet. NAPs provide a neutral point where Internet traffic is passed between different Internet service providers. Remember that backbone providers are also autonomous systems. Connection to and from the autonomous systems uses a border gateway protocol. The most common in use today is BGP4. BGP4 provides a point of demarcation between the backbone provider and the ISP that connects to them. Beyond the border gateway, exterior gateway protocols are used as normal. Again, some examples of EGPs in use today are RIP, RIP2, and OSPF. Despite being a network of networks, the Internet has some structure. At the highest level are the network access points, or NAPs, which are the Internet exchange points. There were originally 4 NAPs, funded by the National Science Foundation. Many other exchanges have subsequently been built. Often, NAPs are referred to as Metropolitan Area Exchanges, or MEAs. MEAs provide essentially the same function as NAPs, but without the funding of the NSF. Since the original 4 NAPs were commissioned, many private companies have built MEAs to fill the needs of the ever-expanding Internet. National and international ISPs connect into these exchange points to do 2 things: exchange traffic with other ISPs, called peering, and sell transit services to other ISPs. Transit services can also be provided by backbone carriers. These backbone carriers do not provide Internet access directly to customers, but carry Internet traffic between major ISPs. For example, eBone provides transit services to over 100 major European ISPs via the largest dedicated IP network in Europe. These international and national ISPs will have regional networks that are used to provide connections to local ISPs. These connections are used to provide transit services for smaller regional and local ISPs who need to send traffic across national and international networks. At the bottom of the diagram are organizations and home users who connect to local ISPs. Connection will be either via dial-up over the PSTN or ISDN, or maybe over some type of high-speed access using XDSL or cable modems. A NAP or MEA is a traffic exchange facility for Internet networks, providing an interconnection point for ISPs to switch Internet protocol IP traffic. The MEAs form part of the Inter in Internet by creating a neutral ground for the interconnection of ISP networks. The MEAs themselves are not interconnected, Therefore, they do not form a network as such. May services should not be considered as Internet connections, but rather a means of inter-exchange for ISP peering partners. Internet access is only possible at the Mays through the use of bilateral or multilateral agreements with other ISPs. In 1993, the NSF awarded the status of Network Access Point, NAP, to WorldCom's May East exchange point outside of Washington, D.C. May East connects many of the major ISPs, as well as many European providers. May West is located in San Jose, providing an exchange point for major ISPs on the West Coast. A complement to May East and May West, May Central in Dallas, Texas, is the newest Tier 1 location. NAPs also exist around the globe, with many in Europe and Asia. Just as a May is not an actual network, it also is not a router, but rather a switching facility. ISPs pay for ports on the May switches and the circuits leading into those ports. The routing function is performed by equipment owned and managed by the ISPs themselves. As can be seen from the schematic, a NAP contains a mixture of high-speed switching elements like gigabit Ethernet switches, ATM switches, and FDDI rings. Each NAP will be unique, depending upon the connections required at that particular site. This map provides locations of current European Internet exchanges. There are now over 30 Internet exchange points located within Europe, all connected by differing backbone providers. Normally, the website of each exchange will provide a list of providers connected at that exchange point. Almost all members of an Internet exchange are backbone providers or ISPs. Occasionally, large corporations will have a direct connection, but this is exceptional. Other users of the Internet exchange points are the academic and research community that have large quantities of data to route between the institutions located in multiple countries. The traffic figures shown here are an example from the London Internet Exchange Point, gathered in June 1999. They confirm peak traffic flows during the working week, with the traffic maintaining its load up to midnight, when home-based users of the net close down their sessions. The annual graph shows the relentless rise in overall traffic, showing a growth factor of somewhere between 3 and 4 times in the year from June 1998 to May 1999. This growth is projected to continue at this rate, and its effects will be examined in the final section. As we have seen, the Internet backbone is a collection of many networks, all connected at interchange points called NAPs. The backbone networks of the international and national ISPs are connected together at the NAPs for the purpose of exchange of data. In the early Internet, the traffic that passed between the early backbone providers like Sprint and UUNet was considered to be balanced in each direction. To reduce administration, the billing of Internet traffic was likewise considered balanced, and no settlement process was required. In 1999, the position has changed. The ISPs are grouped into tiers, and there are usually settlements made between ISPs that are not of the same peer level. If you do not have a peering arrangement with another ISP, then by default you will be classed as a client. Traffic passing from your network to the other ISP will be subject to a tariff, and will incur charges that will need to be recovered from the users of the network. Even within the same peer level, there are settlement agreements being proposed and implemented. Up until recently, there were generally recognized to be 4 Tier 1 ISPs: Sprint, MCI, UUNet, and BBM Planet. Because of the conflict of interest between UUNet and MCI, the MCI backbone was sold in 1998 to Cable and Wireless, when WorldCom completed its merger with MCI. Connections between the ISPs are usually through the NAPs, but in some cases point-to-point links are established between major ISPs to cut down any delay that might be associated with a particular NAP. There are many companies that claim to offer interconnect backbone capabilities. This list shows some of the companies that make such a claim, but even this list is not exhaustive. As we have said, the Internet is a collection of networks. The companies listed here are a snapshot at a particular time of companies providing internet backbones, i.e. with connections into a NAP and a peering agreement with at least one Tier 1 provider. As companies merge or partner in an effort to enhance efficiency, the networks that they operate will often be integrated or sold. The sale of the old MCI backbone to Cable and Wireless in 1998 is an example, driven by regulatory issues with the authorities in the USA and Europe. We all use the acronym ISP, but what is an ISP? All the ISPs added together make the Internet. Without them, there would be no Internet, or a means of accessing the World Wide Web. Put simply, an ISP provides all the facility and function to enable the Internet. They provide a physical means of connection through dial, leased or mobile connections. Through their router interconnection or peering with other ISPs, they provide World Wide Web access. They either rent you or provide a temporary IP address, dependent on your type of connection. They also provide domain name server facilities that enable your browser to find the IP address from the name or URL. They usually offer email hosting, website hosting, and some degree of customer care. Finally, they have the means to bill for their services. These are the basic elements of an ISP. There is no such thing as a typical ISP. Every provider will have a different mix of technology, architecture, and content provision. Generally speaking, there are a number of components that any ISP will have in order to offer Internet services. The first is a point of presence, or POP. A POP is a facility used to house network equipment used in the provision of Internet services. An ISP may have hundreds of POPs worldwide. Smaller ISPs may lease space at the premises of a larger ISP or service provider. The second requirement is a group of network access servers, providing connections to the customer base. A variety of connection types will be offered, usually modem, ISDN, and leased lines being the minimum requirement. Thirdly, some form of LAN switching technology is required to route access traffic inside the POP to servers, to the Internet, or to internal network gateways. Another necessity is a server farm, dealing with user validation and connection parameters. In addition, content servers might exist, providing access to news groups, chat lines, email, and so on. Finally, every international or national ISP will have a connection to the NAP, where a peering point with another ISP can be established. To route traffic that is destined for a different user on the ISP's network, connections to an internal network will exist, possibly via leased lines, frame relay, or ATM. There are now over 50 ISPs in the UK alone that are offering free Internet services. By free, we mean that the user gets unlimited access to the Internet with no sign-up or monthly charges. All they pay are the local call charges for the time spent online. Most ISPs also offer customizable home pages, email addresses, and reliable fast connections to their network. These services are normally sold through retail channels in the high street, typically supermarkets, electronics stores, or newsagents. But how is this service funded? These companies don't offer free Internet services for the benefit of the community. The answer comes from the settlement fees paid between telephone operators. When a call operating from one network is terminated on another operator's telephone network, a settlement fee is incurred. In most of Europe, homes are usually provided with retail telephone services by an incumbent operator. When a call to the Internet is made, the operator routes the call to the network of the ISP, who will terminate the call with an access server connected to their data network. The ISP will recover from the operator part of the call charge that will be levied on the subscriber for this call. From this point on, the call is routed via the ISP's data network toward the Internet as normal. The other method of funding this service comes from advertising revenue. ISPs keep accurate records of the number of eyeballs they have achieved. This is a measure of the number of times an advertisement has been delivered to a PC and been seen by the user. In the US, this phenomenon has extended to free service, and in some cases free PCs if the user takes out a one-year contract with the ISP and commits to a certain amount of time online per month. So how do Internet subscribers in Europe and Asia Pacific gain access to the content providers in the USA that provide many of the latest Internet services like online shopping? Depending upon the size of the ISP that the subscriber is connected to and their target marketplace, there are a number of ways this can be done. For example, in the UK, an Internet exchange point exists in London called the London Internet Exchange, or LINX, and in Manchester called Man App. This is a peering point where many of the backbone providers shown earlier will have connections. For a national ISP, a connection into LINX may be sufficient to provide connectivity to the Internet and connection to other national ISPs. Larger ISPs will have connection to LINX, and traffic between the national ISPs will still route through LINX. Many large ISPs will have their own direct connections into the NAPs in the USA, often May East. Others will use transit backbone providers, such as UUNet, GTS-EBONE, or GTE-BBN, to provide this type of connection. ISPs may also use these backbone providers to carry traffic between the major interconnection points within Europe. In this way, large ISPs can gain access to US content providers without switching through European NAPs. In principle, this should reduce delays and congestion because traffic is being routed more directly between source and destination. Note that a smaller national ISP would still route via their national Internet exchange point, such as LINX. Here they will either peer with a larger ISP or purchase transit services from a backbone network provider to get the necessary connectivity to international content. There are three generic methods of connection into the Internet that organizations or individuals can use. The first is by direct connection to the Internet via a leased line or PVC. A leased line will allow all services to be delivered to the enterprise over the connection, but does have the advantage of round-the-clock connection for the employees and users. This type of connection is a requirement for ISPs, and is becoming more prevalent for global leading-edge businesses and organizations. Typically, connections up to STM1 speeds can be obtained this way. The second method of connection is via an ISP. Access can be via dial-up using modems or ISDN, leased lines, frame relay, or ATM. The benefit of access via ISPs is that a connection method can be selected that matches the user's needs, normally switched access for residential and small business users, and permanent connection for corporate organizations. Another method, becoming less popular, is access via content providers like CompuServe and AOL. These providers normally provide content along with gateways to the Internet, so charges tend to be high when compared to ISPs like FreeServe. Having looked at the generic methods of connection, let's take a look at how the most common physical connection is made using remote access. For most people, Internet access is achieved via a dial-up connection using the PSTN or ISDN. But how does this really work? To the ISP, any call entering their network must be validated so that the user can be identified and billed if appropriate. There are a number of options, but most ISPs use a user ID and a password in most circumstances. There are two password protocols in frequent use. The first is the Password Authentication Protocol, PAP, a simple password protocol that is part of the IETF suite of protocols and transmits a user's name and password across a phone line to a central server for authentication. PAP's password database on the server is encrypted. A user's password, as it travels across the network link, is not. This is considered very insecure. The second alternative is CHAP, the Challenge Handshake Authorization, shown here. When a remote user calls a server that uses CHAP, the server sends back a random challenge to the modem, bridge, or router that initiated the call. Using the key, the remote access equipment encrypts the password and returns it to the server. Password snooping is very difficult with CHAP, since the password is encrypted before it is transmitted over the network. First, a basic communication protocol, the Link Control Protocol, is established, and then, on request from the server, the password is passed to the Radius server for authentication against its database. Assuming the password is OK, the user is allowed access to the Internet, and a full PPP session is established. Radius is very powerful and can limit users to reduced access. Restrictions can either be by time of day, choice of applications, internet addresses, almost anything a firewall can do. The internet infrastructure alone is of little business value without the application tools to breathe life into it. The internet has expanded over recent years to include many applications we now take for granted on our computer desktops today. In this section, we will take a look at the original internet applications, and in particular look at the two main internet applications used today, the World Wide Web and email. How has internet technology affected our daily work? Consider yourself transported back 10 years to the early 90s. Imagine that as a sales or marketing person, you were required to identify some unique features about your product to differentiate it from your competitors. What sources of information would have been available? Well, information would have been available from a number of sources. Maybe technical information could be accessed from a reference library. Getting hold of those research papers would take time, though. A few days by the time you have identified the ones you want, paid for them, and had them posted to you. You could always use the telephone, but that does not always give you the detail you need. Long telephone calls tend to be counterproductive for information research. You could always check out your competitors' literature, assuming you had it in the first place. Today, you can usually do it online in seconds. How up-to-date was that information? Financial information, published in daily papers, was obviously current, but as you move to weekly and monthly periodicals, the sources tend to date rapidly. And how accessible were these sources? Not accessible at all. Today, you can nearly always email info@corporation X and start a dialogue. As we will see, today's internet changes this picture dramatically. Information is readily available on almost every topic and available in seconds. The key issue today is filtering the good information from what might be misleading. The World Wide Web, often known as WWW, has become a worldwide phenomenon, creating a whole new industry of content providers and an explosion of information on the internet. Where other applications rely on your knowledge of internet addressing, hierarchical directory structures, and the application's own, sometimes quirky and arcane set of commands, WWW applications let you click on words or pictures to get where or what you want. This concept is known as hypertext. Often confused with the internet, the WWW is actually the subset of computers around the world that are connected with hypertext. You can think of the World Wide Web as a network of electronic files stored on computers all around the world. Hypertext links these resources together. Uniform Resource Locators, or URLs, are the addresses used to locate these files. The concept developed at CERN in Geneva by Tim Berners-Lee and Associates was originally aimed at making academic research papers more accessible, but the commercial benefits of such a revolutionary technology were soon recognized. It's not just for scientists anymore. What began as a research tool has blossomed into something unexpected and much more fun. With the introduction of graphical web browsers, the web has become a communications tool for a much wider audience. Web pages can include text information, pictures, sounds, video, FTP links for downloading software, and much more. You can create living documents that are updated weekly, daily, or even hourly to give web surfers a different experience every time they visit your pages. As the technology develops, even more amazing and profitable applications will be possible, including those built around e-commerce and e-service. The glue that holds the World Wide Web together is called hypertext and hyperlinks. This allows electronic files on the web to be linked so that you can easily jump between them. On the web, you navigate through pages of information based on what interests you at that particular moment. This is commonly known as browsing or surfing the net. The World Wide Web is built on top of the Internet and uses the TCP IP protocols to transport information between web clients and web servers. Hypertext Transfer Protocol, or HTTP, is the client-server protocol for the World Wide Web. It provides a way for a web browser to access a web server and request hypermedia documents created using hypertext markup language, or HTML. These documents can then be displayed by the browser software. The great power of HTML is that an HTML document can contain hyperlinks to other places in the same document, to other documents at the same website, or documents at other websites. HTTP is responsible for processing these links and providing a common client-server communication protocol that ensures this information can be easily retrieved regardless of the actual computers and software of the sender or receiver. The HTTP protocol can be secured using secure HTTP or some other protocol. Encrypted information is transmitted on a secure channel to prevent eavesdropping. Support of such secure protocols is essential if e-commerce is to become a universal business medium. Browser applications have simplified and revolutionized how people access information. Most sources of information available via the World Wide Web can be accessed by the users through the use of a browser. Browsers now dominate the PC desktop, providing users with access to Internet content providers worldwide. Their success has been due to the widespread use of a single method of encoding information to display on screen, HTML, which has rapidly displaced other proprietary methods used in the 70s and 80s, like IBM's 3270 and DEC's VT220 standards. A web browser is a program which is used to visit web pages. Simple to use, a browser works by hiding the complexity of the TCP/IP stack that resides on the user's PC, making access to the Internet as simple as clicking a mouse button. Netscape Navigator and Microsoft Internet Explorer are the two most well-known web browsers, which are now used by the vast majority. Netscape and Microsoft Internet Explorer have pretty much the same features and are available for many different operating systems. You can also add help applications to a browser. These are usually called plugins. A plugin is used by the browser when it encounters a special kind of file that it is unable to decode, one that is not written in HTML. For example, a user might connect the browser to a website that is an internet radio station with live broadcast. During this connection, the browser will receive a stream of data, maybe in real audio format, and will start up a real audio plugin to decode the information and play the radio channel through the PC speakers. Both Netscape Navigator and Microsoft Internet Explorer are currently free and feature HTML 3.2, Java, JavaScript, and various extensions that may or may not work with other browsers. Also included are a suite of additional applications for conferencing, reading news groups, and for receiving and sending email. Java is a language developed by Sun Microsystems which allows World Wide Web pages to contain code that is executed on the browser. Java software runs in many places, on many kinds of computers and devices. Perhaps the most visible examples of Java software today are on the Internet and on enterprise networks. They're nimble, interactive programs called applets. Applets work inside web browsers on computers and other devices. Here's how it works on a desktop computer in a web browser. References to Java software are embedded on a web page. This page can be stored on the network or local disk. When the web browser sees these references, it loads the Java software, called an applet, transparently and securely. The applet is then processed by the Java virtual machine, which is built into the browser. The Java virtual machine first does stringent security checks, and then runs the applet, which appears and interoperates inside the browser. Because Java is based on a single virtual machine that all implementations of Java emulate, it is possible for Java programs to run on any system which has a version of Java. It is also possible for the virtual machine emulator to make sure that Java programs downloaded through the web do not attempt to do unauthorized things. There are other kinds of Java software. Java programs can run directly on your computer without requiring a browser, or on servers, on large mainframe computers or other devices. It's been said that the Internet is like a huge public library with no card catalogue. With hundreds of millions of web pages online, users could spend a lifetime surfing the web, following links from one page to another. Amusing perhaps, but not very efficient if they are after some specific information. One of the biggest complaints about the Internet concerns the difficulty of targeting information. Where do you start? Searching the Internet requires part skill, part luck, and a little bit of art. Fortunately, a number of free online resources can help users with the hunting. Search tools represent the efforts of many individuals and organizations to improve access to information on the Internet. Each one is organized or searches differently. You've probably heard of Yahoo, Lycos, Excite, Alta Vista, and other so-called Internet search engines. There are literally dozens of these tools to help users locate what they're looking for. The trick, though, is understanding how they work, so surfers can use the right tool for the job. Search engines can provide two types of searches, directories and indexes. Directories are good at identifying general information. They group websites under similar categories, such as Internet tutorials, English universities, and Paris museums. The results of the surfer's search will be a list of websites related to the subject they are searching for. If they are interested in locating the site for the Louvre Museum, for instance, they would use a directory. But let's say the surfer wants more specific information, such as biographical information about Leonardo da Vinci. Web indexes are the way to go, because they search all the contents of a website. Indexes use software programs called spiders, or robots, that scour the Internet, analyzing millions of web pages and newsgroup postings, indexing all of the words. Indexes find individual pages of a website that match the requested search, even if the site itself has nothing to do with what the surfer may be looking for. Surfers can often find unexpected gems of information this way, but they must be prepared to wade through a lot of irrelevant information too. Search results are usually ranked in order of relevance, the number of times the search terms you used appear in a document, or how closely the document appears to match a concept the surfer has entered. You can think of the World Wide Web as a network of electronic files stored on computers all around the world. Hypertext links these resources together. Uniform Resource Locators, or URLs, are the names, and indirectly the addresses used to locate these files. The information contained in a URL gives you the ability to jump from one page to another with just a click of your mouse. Whether you type a URL into your browser or click on a hypertext link, your browser is actually sending a request to download a file stored on a remote computer. The first part of a URL, before the two slashes, tells you the type of resource or method of access at that address, for example HTTP. The second part of a URL is typically the address of the computer where the data or service is located. Additional parts may specify the names of files, the port to connect to, or the text to search for in a database. You can enter the URL of a site by typing it into the location window of your web browser, just under the toolbar. If someone gives you the URL address to their web page, they may say it's at www.learnthenet.com. Today, most browsers assume that you want to visit a web page, so you do not need to include http:// at the beginning of the URL. However, remember you can also connect to FTP sites and gophers with your browser. So, for example, you will need to be specific if visiting an FTP site, which always begins with an FTP://. One of the smart things about URLs is that you don't have to keep local copies of documents. They only live at the source on the server, and any time you need to see them, you retrieve or download a copy of the latest version, assuming the server system is awake and you can reach it. In the past, people shared around many copies of online documents, and they developed elaborate schemes to try to ensure the latest copies were always distributed to all users. The World Wide Web, and particularly company intranets, have removed the need for complex document version tracking in many of today's business applications. Most web browsers cache local copies of files for a while. If you visit a website and return to it, often the return is pretty fast because a temporary local copy of the file is used. Many ISPs also now cache local copies of the most frequently visited websites on servers at their premises. This can help significantly to speed up internet response times. Domain naming, and its most visible component, the domain name system, is critical to the operation of the internet. The average European phone number with area code is 9 or 10 digits in length and encodes 10 to the power 10, or 10 billion possibilities. The Internet IP address at 32 bits encodes 2 to the power 32, or 4.2 billion possibilities. For humans, it is impossible to remember all these combinations, so how can we build an effective directory of these difficult large numbers? The telephone company solves this problem with lots of large paper directories, and operators you call and ask about numbers not in your directory. The Internet answer is a hierarchy of simple mnemonic names, called domain names. Instead of remembering an IP address 205.216.138.22, all you need to know is the host's domain name, e.g. sirius-uk.com. Some people think the dots in a domain name correspond to the dots in the numeric address. This is not the case. There are always 3 periods in an IP address, separating its 4 constituent bytes. This is not the case in a domain name, where there may be a variable number of periods. The naming system is hierarchical in structure. The tree has a topmost root level, and major divisions called domains branch from the root. In the diagram, not all domains are shown, specifically those for other countries such as .co.uk or .fr. Only the top-level domains are listed here. An ISP is probably part of the .net domain, while a company is probably part of the .com or its local national domain. In February 1997, the IAB announced 7 new generic top-level domains, in addition to the existing ones of .com, .net and .org. The new fields are .firm, for businesses or firms, .store, for retail, .arts, for culture and entertainment, .rec, for recreational entertainment, .info, information services, and .nom, individuals or personal nomenclature. As we have already indicated, people like to reference locations using names, often with associated meaning to the type and place where the location resides. Computers, on the other hand, like addresses in the form of numbers. Domain Name System, or DNS, is a way for computers to share information about computer names and addresses. On the Internet, this is a lot of information. In techie terms, DNS is the name and address resolution service used on the Internet. In more straightforward terms, DNS is a kind of distributed directory service. It searches for and finds the numeric Internet address for a given URL. Today, DNS has to be distributed. Can you imagine the size of disk required to hold all the names and addresses used on the Internet? A named server and a DNS database is most often maintained by the user's Internet service provider. In some larger organizations, a local name server and DNS database may be maintained of the most frequently used addresses. With the DNS, the capability is in place so that a user can obtain the necessary IP address from a domain name or URL. Consider that when a user wishes to connect to a given site, such as www.sirius-uk.com, the Internet client application, such as a browser, needs to obtain the IP address before any communication can take place. This process is controlled on the user's PC by a TCP/IP program known as a resolver. The resolver takes the client's program's request and converts it into a query to a name server. The name server looks the URL up in its DNS database and determines that the IP address of www.sirius-uk.com is 205.216.138.22. This is then returned to the client program via the resolver. In fact, the scenario is usually a bit more complicated than a simple query response. When a client application needs to learn the address of some host system, the resolver sends an appropriate message to the ISP's local name server. If the requested name is not in the ISP DNS database, it is the local ISP's name server's responsibility to forward the request to other name servers until the request is satisfied. When the address is found, the name server updates its DNS database. Only when the URL name has been translated to an IP address can the client application try to connect to the destination system via standard TCP/IP procedures. The domain name server, the local resolver, and the protocols used to resolve a name into an IP address are all specified in the TCP/IP protocol suite. Let's look at a typical dialed call setup, from a user typing in a URL to receiving the first page. Much of the process is hidden from the user, and there are some variations dependent on how the ISP provides the functions. In the first step, the user is authenticated. This is handled by a radius server using either PAP or CHAP authentication protocol between the user PC and a radius server at the ISP. Often the IP address of the DHCP server is supplied at this stage as part of the setup routine. Once authenticated, the user needs an IP address. This can be provided using many mechanisms, including bootp and user lists, but a common mechanism is DHCP, which provides high levels of automation. The DHCP server provides a temporary IP address to the user PC, as well as providing the IP addresses of the DNS server and the default gateway. The user enters a website URL into their browser and hits the Enter key. The browser needs to find an IP address that corresponds to the URL, so it needs to connect to the DNS server. The DNS server searches through its cache to see if the URL exists there. If not, it broadcasts onto the web for a URL IP address match. Once the DNS server has an IP address match for the specified URL, it passes it back to the user PC. The browser puts the IP address received from the DNS server into the destination address field of the IP packet, and sends it to the specified default gateway router. The default gateway router looks at the destination address and searches its routing tables for the best route at that time to send the packet on its way through the web to its destination. Most office workers today use Internet technology as part of their daily routine in the form of email and Internet browsers. It is worth taking just a few moments to look at exactly how fast this new technology has been introduced into the office environment, and how this has benefited companies that have taken the new applications on board. If we cast our minds back to the 1970s and early 80s, the standard method of written intra-office communication was the internal memo, usually typed and copied either with carbon papers for up to 4 copies or an ink duplicator for multiple copies. Obvious drawbacks of this were that the creative process, typing, was slow and inflexible. The duplication process was cumbersome, and the distribution system was manual. Altogether, an extremely time-consuming process. Production of documents like contracts and product documentation was equally awkward, resulting in thousands of man-hours being consumed in the production process, rather than being used in the creative process. During the 80s, office communications changed radically with the introduction of post-it notes and computers. No longer were we confined to typewriters and carbon paper. photocopies and post-its generated more paper than we could ever have dreamed of. This was so prolific that it sparked off numerous environmental groups mandating the protection of trees and the environment. However, for the office, the trend was set: small memos with widespread distribution. It was after the advent of computer word processors that things started to really take off. PCs now produced multi-page documents easily, but it still wasn't that easy to get that spreadsheet over to Joe in accounts. SneakerNet, hand delivery of electronic documents stored on floppy disk, was born. Today's email has all of the attributes of the above technologies, but delivers information quickly and efficiently to anywhere in the world, without the mess associated with printer-based duplication systems. Electronic mail, once the exclusive domain of the keyboard, can now be handled through graphical user interfaces with a combination of mouse and keyboard. There are many email clients available today. Simple clients that build into browsers such as those in Netscape Navigator and Internet Explorer, and purpose-built applications like Eudora, CCmail and Microsoft Outlook, shown here. The primary use for email was to speed up communication between users, firstly in the academic environment, but email has now spread into an application that serves all communities of interest worldwide. Compared to traditional postal services, email brings speed, efficiency, and huge cost savings to any enterprise that uses it appropriately. Electronic attachments, like documents, sound clips, or video, make the application even more useful, as it is now possible to deliver documents to somebody on the other side of the world in seconds. Attachments can be made to emails that enhance its use dramatically. Attachments can be in plain text, spreadsheet format, word processing document, or even binary files. Standards for encoding and decoding the attachments have become universal, so it is rare to receive an attachment that is undecodable these days. Two common standards for encoding and decoding attachments include UUEncode and MIME. All these applications rely on a post office to handle and route mail. As with older email readers, you can read incoming mail, sort mail into different folders, save it, delete it, or forward it onto another user in the same post office or anywhere on the internet. With outgoing mail, you have the same degree of flexibility. Email and SMTP, Simple Message Transfer Protocol, should not be confused. Email is an application offering mail services that operates on a PC or other host computer with a user interface. SMTP is a protocol intended for the transfer of message elements across an IP-based network, like the Internet. Email applications will use SMTP to deliver message elements from one mail server or client to another. As an email administrator, you will need to be aware of different email server types. The most common is the Post Office Protocol, POP3, which provides mail server functions. The mail server name will often be the host name, preceded with the word mail. The outgoing mail server type is usually classed as SMTP. IMAP is a new post office protocol, but unlike POP, it is designed to put most of the email processing workload on the server. At this time, the client interface is limited, and most ISPs will continue to use POP until IMAP matures. Where email is operated over a switched network, as opposed to direct connection via a LAN, then it is usual for the email provider to ensure that user validation is completed prior to connection to the server. Two protocols are in use. PAP, Password Authentication Protocol, is the most popular, and CHAP, the Challenge Handshake Authorization Protocol. Once validated, the email client will establish a connection, usually using PPP as the Layer 2 protocol, to the email server, and a dialogue will occur between server and client to transfer email information. This exchange will use SMTP as the transfer protocol. The File Transfer Protocol, or FTP, is used to browse FTP servers and to transfer files to and from those sites. Most users of the web use FTP without necessarily realizing it. An FTP client resides on the user equipment and communicates with an FTP server on another machine that manages the client requests. Today, most current browsers like Netscape or Internet Explorer have FTP clients built in, and we often use these without noticing. An FTP site is any site where groups of text, graphics, binary, video, in fact any kind of file, are organized into a directory structure where users are permitted to gain access. FTP is a connection-orientated protocol, meaning that a connection is established prior to file transfer. Connection establishment may also require authentication, as there may be information on the FTP server that is restricted to specific user groups. These groups will have a unique password, which is passed from client to server during session establishment. Often, FTP sites are accessed through using the anonymous login, hence the term anonymous FTP site. No password is required for these sites. For reliability, FTP uses the TCP protocol for connection management. This provides some degree of security and a reliable, error-free data transmission path. Another protocol, TFTP, is a simplified file transfer protocol and uses UDP at its transmission layer. TFTP is mostly used with messaging systems like email. FTP server processes are often called daemons, abbreviated to FTPD. FTPD software is freely available on the open market. Newsgroups were born in the academic world of the universities. User groups needed to share information and used postings that anyone could read and respond to. Nowadays, your email client is also a newsreader, and you can use it to subscribe to, read messages from, and post messages to newsgroups and have online discussions on practically any topic. From a business perspective, the most useful newsgroups are ones dealing with financial information, where opinions are openly expressed and exchanged, and technical newsgroups dealing with standardization issues. Each newsgroup covers a particular topic, often alluded to in its name. A newsgroup is really a discussion string comprised of a series of related messages. Each message responds to an earlier message or addresses the overall newsgroup topic in some way. You can post your own message in response to the messages that interest you most. You can find newsgroups that may interest you by searching for them through the Deja News website. Together, newsgroups make up Usenet, which can be thought of as part of the Internet. Today, there are thousands and thousands of newsgroups on every topic imaginable. Each service provider decides how many of the newsgroups it will make available, but most have at least a few thousand to choose from. Newsgroups are where the terms spamming, useless or blatantly promotional messages posted en masse, and flaming, a torrent of angry replies to a message, originated. If you spam a group, you're likely to get flamed. To find out more about newsgroups, try out www.zdnet.com/products/newsuser/. IRC is the original chat medium on the Internet and is still the most widely used means of chatting with people around the world. IRC is worldwide. More than 100,000 people are online chatting at any given hour, 24 hours a day. IRC networks vary in size. Smaller ones may have as few as 2 servers and less than 100 users. Others, like EFnet, can have over 100 servers and more than 20,000 users. An IRC network is a collection of servers connected together. When you log on to an IRC network, you are connecting to one of the servers on that network. Since all the servers are connected to each other, you are connected to all the other users, even though they may not be connected to the same server as you. All servers on a network share and have access to the same information. Each server knows who is on the network, what channel that user is on, and which server the user is on as well. There are many IRC networks. Each network is a separate entity unto itself. One network does not connect to another network. The networks do not share common servers. You cannot talk to a user that is not on the same network as you. If your friend is on the Newbies channel on EFNet, and you are on the Newbies channel on DALNet, you cannot talk to him because he is on a different network. So, if you want to meet a friend on a particular channel, make sure you are both on the same network, or you might find yourself needing to join multiple networks. Check out www.newircusers.com if you want to find out more. Businesses seeking a large or sophisticated web presence can outsource their website to a service provider offering hosting services. Hosting enables corporations to move business-critical internet applications off-site for improved bandwidth, reliable connections, and for better security. Most companies outsource their applications because they think that they don't have enough internal resources to host applications in their own building. Companies can't or won't fill the gap in IT skills. The hosting market is growing at a tremendous rate globally, at 80% CIDR in the USA and at 70% CIDR in Europe. The hosting market in Europe is predicted to be worth over $500 million in 2000. It spans the whole range of potential customer segments, from the large corporate customers to the small to medium enterprise. A key part of any hosting service is the telehouse facilities. These are very large buildings with dedicated power, high security, and 24-hour support. They house customers' own servers, as well as supporting customers' applications on server hardware supplied by the service provider. Key to the facility's success is the provision of higher concentration of network bandwidth per square meter. Each rack can have well in excess of 2 megabits per second of bandwidth for connection to the internet backbone, and there could be many hundreds of racks within any one telehouse. Network connectivity is provided either into the internet or into private networks. Internet connectivity can make use of transit services and can also support a whole array of access services from PSTN dial to ATM. A service provider may offer co-location services. The customer locates their own server in a service provider data center. The service provider provides bandwidth, power, and a connection through to an IP network, what is known as pipe, power, and ping. The service provider provides basic management of the server, but the customer is responsible for it and the applications that they run on it. To ensure reliable operation, remote management options are usually available. Different co-location options can be provided. Many customers are willing to locate their servers within racks shared among many customers. However, for other customers, particularly those with e-commerce applications, dedicated co-location within secure cages or suites is required to ensure application security. As the site is normally used by many and various customers, security of both the site and the equipment within the site is critical. Most service providers provide 24-hour access, but this is often controlled by sophisticated security systems, including CCTV cameras and swipe card entry systems. As an alternative to co-location services, a service provider may offer hosting services where they provide and maintain the physical server hardware. Two very different hosting solutions may be provided by a service provider. With a shared hosting service, the customer puts their applications on a server provided by the service provider. This is located in a rack in a telehouse. The server also contains applications from other customers, each securely segregated. The server has an amount of bandwidth connected to it, shared by all of the customer applications, with access to an IP network and/or the internet. More comprehensive server management is provided, as the carrier is responsible for the server, but the customer is fully responsible for their own applications. To meet customer needs, multiple computer operating system environments must be supported. NT, BSD Unix, and Solaris are the three key environments. The biggest selling platform is NT. The alternative hosting service is to provide dedicated hosting. With this service, the customer has their own dedicated server in a rack. The service provider is responsible for management of the server, but the customer is responsible for their applications. Dedicated bandwidth is connected to the server with connection to an IP network and/or the internet. Again, multiple computer environments must be supported. To provide the required level of service most users require, sophisticated 24-hour management systems must be provided, including monitoring, disk mirroring, nightly tape backup, and online usage reports. As the applications are still managed by the customer, 24-hour physical site access must also be provided. With the phenomenal growth in e-commerce, both business to business and business to consumer, there is a growing demand for service providers to extend their capabilities to include application hosting services. The application service provider, or ASP, provides a server in a rack and installs and manages applications, whether Microsoft Office, e-commerce or ERP applications like SAP and PeopleSoft. The service provider provides bandwidth to the server with connectivity to an IP network. The customer pays to access these applications via either the Internet or a private IP VPN. Traditionally, there have been two types of player in this market, the network company and the application company. Both have offered services based on their core strengths, but over time they have both encroached into one another's areas of expertise in the rush to meet growing customer needs. Currently, telcos are offering network services and some application services. Application providers are offering application services and some network services. There is an obvious conflict and confrontation between these organizations, as they are both playing in each other's areas of strength. As the market develops and more new players become involved, the competitive pressures increase. This is forcing some companies to focus on their core strengths, and hence we are starting to see a convergence in the market, where application providers focus on applications and network providers focus on networking, co-location and hosting. However, we are also seeing strong collaborations between networking and application companies to try and provide a one-stop shop for various types of clients. Imagine a paperless newspaper consisting of 5 megabytes of text, sound and video clips. Imagine a circulation list of 10,000 subscribers for this service. Unicast and multicast are two different methods of distributing this information to the subscribers. We will see that multicast transmission affords many advantages over unicast transmission in a one-to-many or many-to-many environment. In the case of unicast transmission, multiple clients accessing an application on a server will each receive their own copies of the frames associated with that application, even though every client will receive identical frames from the host. This leads to duplication in the network, with many copies of the same frame being transmitted, one per user. A multicast network offers optimized performance for the network because less copies of data require forwarding and processing. A single frame sent from the host will be duplicated by the network at branching points. Using the network to duplicate frames is more efficient than duplication done by the server application. In the top graphic, we can see that the traffic level and clients increase at a 1-to-1 rate with a unicast network, whereas in a multicast environment, traffic levels and clients increase, but at a greatly reduced rate. In this way, a multicast network provides enhanced efficiency. Available network bandwidth is utilized more efficiently, since multiple streams of data are replaced with a single transmission. Let's look at advanced multicast services. Several applications that make good use of multicast have been defined. Session Directory is a tool that allows participants to view advertised multicast sessions and launch appropriate multicast applications to join an existing session. Video conferencing allows multiple participants to share video and audio interactively. Audio conferencing allows multiple participants to share audio interactively. Whiteboarding allows multiple participants to collaborate interactively in a text and graphical environment when sending the same data to multiple receivers. Whiteboard uses a form of reliable multicast. To design and refine these multicast applications and protocols, an experimental system called the IP Multicast Backbone, or MBone, was created in 1992. In 1992, the IETF sponsored the first audio casts of their sessions, and by 1997, the MBone had grown to 3,400 subnets in 25 countries. Today, that number has exceeded 7,000 subnets and is becoming a fast-growing area of the Internet. The M-bone provides islands of multicast capability, but still relies on the Internet backbone to provide basic IP transmission services. The M-bone is sponsored by multiple vendors that all supply equipment capable of supporting multicast transmission protocols. A firewall is a way of providing security of information and private network resources, preventing unauthorized use, in much the same way as a fire door protects against fire. A firewall is more intelligent and flexible than a simple barrier, though, as it allows valid users to gain access to predefined network resources. Without firewalls, the ability of users in a corporation accessing the Internet would also imply that Internet users would have access to the corporate network. That is, the corporate network would be open to access from anyone in the Internet address space. As we can see from these statistics, this is unacceptable, as severe damage, both technical and commercial, can be done during unauthorized access. Firewalls are designed to protect against this threat by identifying all traffic passing into and out of the corporate network. Firewalls need to be added into the network wherever access from the Internet is possible. A single firewall at head office will not provide sufficient security if there are other branch offices on the network with gateways to the Internet. Firewalls are physically located in the routers connected to the Internet lines, or in standalone machines. Often these are Sun SPARC running only firewall software. Physical security to these systems is also usually deployed, so that modifications to the firewall configuration are restricted to a few identified personnel within the organization. Firewalls are sophisticated security systems that are designed to filter packets and have many configuration options to support the user needs. Firewalls can operate at different levels in the TCP/IP stack, giving network designers a great deal of flexibility in the design of the security system they are building. For example, network address filtering is used to identify the source of the packets entering the intranet. This might seem to be effective at first sight, but there are ways to spoof source IP addresses, allowing a hacker to appear as a permitted IP user, so this technique is usually employed along with other filters. Filtering on a specific transmission layer protocol is possible by identifying the socket number of the protocol in the IP packets. In this way, access to probes like ping and traceroute can be denied. This will stop hackers probing around a corporate network, identifying resources, host addresses, route table entries, and so on. Probably the most powerful firewall method is to filter at the application level. Application-level filtering makes it possible to filter on the specific application using any of the underlying protocol stacks. This allows network designers the ability to switch off individual applications based on the needs of the users or the corporation. An example of this has been the removal of point-cast information push applications which potentially use a lot of network bandwidth. Due to the massive growth of the Internet during the last 3 years, many doubts have been expressed regarding its ability to scale sufficiently in order to meet the growth curves being predicted by the analysts. Overwhelming demand is still being generated by new content providers and application offerings. This section aims to illustrate the issues associated with burgeoning traffic and users, and the diversity of business and home applications being introduced as we enter the new millennium. There are several significant challenges for the Internet. This final section deals with performance-related challenges. In an ideal world, a premium connection would be at a high price, an entry-level connection would be at a low price, and you could pick the level of goodness based on your ability and willingness to pay. In the chaos that is today's Internet, this is almost impossible to guarantee. At the backbone level, where you are located can make a difference to the level of performance you get. Generally, backbone providers have backbones operating at 34, 45, or 155 megabits per second. From each node on this backbone, other cities are serviced with smaller 2 megabit lines, E1 lines, or often multiple lines operating at 2 megabits per second. If you are in a specific city that is a major node operating at 34 megabits per second for one service provider, but a minor node with 2 megabits per second service for another, you would probably be attracted to the ISP offering the larger node, particularly if you were looking for a high bandwidth connection for your business. When considering the access connection, there are many alternatives to a standard dial-up connection coming onto the market today. Traditional modems operate at speeds up to 56 kilobits per second, using the latest V90 specification. But technologies like cable modems and XDSL are extending these access speeds into the megabit range. Different ISPs will offer a different selection of access methods, so it is important to check their product offering if high-speed internet connection is needed. Taking the example of the previous graphic a stage further highlights another potential issue raised by the current design of the Internet, where there is no concept of quality of service, or QoS. By QoS we mean guaranteed response time, throughput, or jitter. In the Internet world, the ISP makes a profit by connecting as many users as possible onto his network. Network trunks are oversubscribed in order to maximize profits. In practice, this might mean that the access connections from the regional router might operate at 2 megabits per second, but 100 user ports are available for users to connect at 56 kilobits per second, a total of 5.6 megabits of traffic if all users transmit simultaneously. This represents an oversubscription of 2.8 times. In the access POP, oversubscription of 20 to 1 is quite usual, and on the backbone network, oversubscription factors of 4 to 1 are quite common. Oversubscription translates into delay for the user, as packets get queued up in routers waiting for their turn to be transmitted by the network. All this means that a high-speed connection does not necessarily mean high performance. It can do, but the level of oversubscription is also critical. Sometimes, if performance is poor when dialing into a major city hub, it is worth considering dialing into a regional hub if the ISP operates multiple hubs, where there may be less users logged onto the Internet. The Internet is predominantly constructed from multiple router-based networks. The design traditionally involves many small, low-end remote POPs being fed into a regional location. Several routers will be used to provide termination points for those routers. These routers will then be connected to a backbone router. The backbone routers are usually mesh connected to other backbone routers using some high-speed connections. The topology of the network will be spoke and hub, like a bicycle wheel, for remote router access, and mesh, like a spider's web, for backbone router interconnections. There are some issues with this type of design as the network grows or scales. Firstly, the amount of CPU processing required for route table lookups, routing, firewall control, etc. increases dramatically, leading to increased cost of equipment. Secondly, latency and queuing increase, resulting in no deterministic quality of service, particularly for business users. This precludes them running money-saving schemes like voice over IP or reliable streaming video applications. There is limited congestion management, although some vendors implement different queues for different packet classes. This again takes a lot of processing power. And finally, there is usually limited route table space. As the Internet scales, the routers dealing with the BGP4 gateways need to hold extremely large route tables. The current size of the Internet route table is around 40,000 entries, and searching route tables of this size introduces latency once again. It has proven difficult to achieve sustained profit from the provision of basic Internet services. ISPs are looking to relatively short periods of return on investment for any new infrastructure purchased. Business customers are developing more business-critical applications that operate over the Internet. These generally require a better service from the Internet. Business customers are willing to pay for what they need, and this requirement is driving the introduction of classes of service within the Internet. There are a number of technical solutions being promoted to achieve classes of service for the Internet. The three main solutions are Layer 2 switching, provided by the ATM or frame relay, multi-protocol label switching or MPLS, which includes proprietary solutions like tag switching from Cisco and resource reservation protocol, also known as RSVP. Level 2 switching and MPLS are receiving the majority of attention as there are concerns about the scalability of RSVP. We will look at MPLS in a little more detail in the next slide. All of these solutions have the ability to provide a specific user with an individual class of service. This allows that user to be grouped into a predefined service class, rather like an airline system provides first, business or economy classes of service, each with an individual tariff. Coupled with this is the potentially lucrative outsourced intranet market that is starting to become a reality. There is also a desire to consolidate other data services with the Internet to provide a full range of data-orientated service to business customers. The chase for new revenues is fueling investment in Internet service backbones, increasing network bandwidth and reducing network latencies. Many vendors have attempted to tackle the quality of service and performance issues. Issues like scaling virtual circuits, the N-squared problem, become major technical headaches as networks grow. MPLS is emerging as one of the mechanisms that provides an ability for service providers and ISPs to provide better and multiple service qualities. The IETF are attempting to consolidate several initiatives that have come from the vendor community into a single consolidated standard that includes the best elements from each approach. For MPLS to become adopted and universal, many of the key service providers will need to adopt or enhance MPLS and physically implement the standard in their networks. MPLS works by defining a path through the network with defined characteristics like throughput, delay, and maybe jitter. To do this, the user has to signal to the network what kind of data he wants to send, and the service parameters that data will require from the network. Wherever possible, the network will establish an MPLS tunnel through the IP network that meets the required quality of service, and all subsequent data packets associated with that connection will be sent over this path. This differs from the current Internet, where the path taken by packets between source and destination can vary. Devices called edge switch routers label each IP packet with a short label at ingress to the network, and this tag is used to switch packets in the network, much in the same way as ATM or frame relay switches already do today. At the egress point, an edge switch router removes the labels and passes the IP packet onto its destination. There is an exponential growth in the volume of data traffic carried on carrier networks and the Internet. There are more users, and most of these need to send ever-increasing amounts of data traffic. Voice traffic is growing linearly in Europe, although only at a 3% CAGR, compared with data traffic which has a CAGR of 42%. At some point, the volume of data traffic will overtake the volume of voice traffic carried on carrier networks. Many predictions indicated that this would occur around the turn of the millennium, although BT reported that it happened in their UK network in 1998. As a result, these carriers and ISPs are looking at being able to carry all applications using IP, and this includes voice as well. Now, voice over IP requires some specific components to be implemented. The most important are the gateways and the gatekeeper. The gateways convert voice on 64 kilobits per second PSTN lines into IP packets and back again. The gatekeeper is the central intelligence and controls call setup and advanced features. Carrying voice over IP allows voice transfer rates to be reduced from 64 kilobits per second to as little as 6 kilobits per second. However, this does have some potential drawbacks. Voice over IP needs a very stable IP network with very low delay characteristics. As a result, voice over the Internet isn't a very good solution until quality of service capabilities are deployed. There are a number of technical issues still being worked out, but voice carried over a well-engineered IP network can achieve a very good quality level, and certainly good enough for business applications. The most important point about voice over IP is what it will be used for. There is a popular misconception that it will be used as a total replacement for existing voice networks. This is based on the fact that some carriers are today offering voice-over IP calls at lower rates than traditional PSTN networks. The business model for cheaper voice calls isn't sustainable in the long term, and the reality is that most major vendors and service providers see the future of voice-over IP as a means of enabling voice and data integration at the desktop. New applications such as the IP PABX and the web-enabled call center are two examples of this. Most web browsers have a very simple approach to networking. Given a URL containing a host name and an item on that host, they make a TCP connection to the named host and retrieve the specified item. If the host cannot be reached, the user will receive an error message instead of the page requested. Since browsers and their users are independent, there is a huge amount of replication in the information carried over the network. Every user gets their own copy of every page they request. Web caches are an attempt to reduce this wastage. By intercepting parallel requests, a cache may be able to serve copies of the same document to a number of users from only a single connection to the remote site. To achieve the greatest reduction in network traffic, this merging of individual requests should be performed as close as possible to the users. When a cache receives a request, it compares it against other recent requests. If the same URL has already been fetched from its source, and provided a copy of the resulting document was kept and is still available, then the new request can be satisfied immediately by replying with the local copy. Otherwise, the cache will forward the request, either to the host named in the URL or to a parent cache, and return any response to the browser. However, it is important to remember that information gets out of date very quickly on the Internet. Caches deliberately age. Depending upon implementation, the cache will flush out pages older than a certain age. As to how useful caching can be, especially considering the size of the Internet, is a different matter. With a small cache, a couple of gigs of disk space, the returns are remarkably high, up to 25%. This space caches the very often accessed sites, such as Netscape, CNN, and some of the other high-hit sites. And finally, the Internet continues to grow exponentially, and application types are expanding, with new software coming online every day. Internet scaling issues are becoming critical, and ISPs that are now offering low-cost or free Internet access will continue to drive the trend. Some of the newest Internet applications are voice over IP. The media industry use of IP for web radio and web TV. E-commerce and the effects the web will have on the way we buy and pay for products and services. And finally, new leisure activities such as e-gambling and particularly e-gaming. These are discussed in more detail in the future IP services module. Thank you for taking the Understanding the Internet training module. We hope that you have now gained a vision of some of the basic technologies and applications being used within today's Internet. Thank you for your time.